In this video, I'm going to talk about the rates of weathering. We have already discussed that there are two types of weathering: mechanical, or sometimes called physical, and chemical weathering. Mechanical weathering is the breaking down of rock material into smaller sediments, but those sediments have the same chemical composition as their parent rock. But with chemical weathering, we also learned that these smaller fragments have a different chemical composition. So those rocks were broken down and have a different chemical composition than their parent rock. We also discussed different types of mechanical and chemical weathering, and also went into the lab area and did some work and trying to figure out what reactions and what activities were demonstrating the different kinds of weathering that we were discussing. So with this video, we're going to be talking about rates of weathering, how fast or slow the weathering will be of a particular rock. And there are three major factors that affect this rate. And the first one is what we have is climate. Climate plays a huge role in determining what type of weathering that's going to occur. Climate is defined as the area's overall temperature and rainfall. And if you look at the pictures here, we have a tropical forest. In this region, in the tropical areas where they're getting a lot of rainfall and the overall temperatures are very high, they will get a high rate of chemical weathering occurring. So all of the rock material that is breaking down in that chemical composition it's different than the original. In the bottom picture here, you can see this arid climate where the overall temperature is probably fairly warm and sometimes maybe even cool, but you can see that there is a lack of water here. So the type of weathering that's going to be dominant in this area is physical weathering or our mechanical weathering. One of the things that you want to remember is that as the temperature and the amount of rainfall increases, you'll get more and more chemical weathering occurring in that area. So now let's take a look at this graph that you have here, weathering determined by climate. And here you have average yearly temperature, and you can see this is in Celsius, and along this axis you have average yearly precipitation in centimeters. And you can see all the various different kinds of mechanical and chemical weathering here. And how you read this is you take a look at the question and you look for the average temperature, and then you go up to what the average precipitation is for the area and see what region, what area that it's in. So for example, this question says, what type of weathering is most common where the average yearly temperature is 0 degrees Celsius, so that's here, and the average yearly precipitation is 100. So all the way up to the graph, and where they intersect is in the moderate chemical weathering with frost action. So meaning they're having pretty much both types of weathering occur in that area. The second question says, which climatic conditions would produce strong chemical weathering? So you go through, and the best way to do these kinds of questions, if they were on a Regents exam or quiz or test, is you start to do process of elimination. We are looking for strong chemical weathering. So let's start with the first one, -5 Celsius. And we're here, and the average precipitation 75. That is in moderate frost action, not what we need. So come over here to 10, up to 50, and we're on the cusp of moderate chemical weathering and the moderate chemical weathering with frost action. Keep moving up to 15, all the way up to 100. That's your moderate chemical weathering. And if we keep going up to 25, up to 175, we can see the strong chemical weathering. So the answer for us would be choice 4. At the end of this recording, you're going to be asked to complete a worksheet and further use this graph in practice. So the next factor that affects the rate of weathering is the particle size. And here in this diagram, you can see a particle. And here, when you put water, acid, whatever the type of chemical or such that's going to attack the surface, it's got all these different ones to try to break down. But as soon as you go and take that particle and break it into smaller pieces, now you've increased the surface area and you've given more surface for the chemicals to attack it, or let's say water to attack it. And then again, continuing to break that down, you're increasing the surface area. So if you were to take this and put it in, let's say, vinegar. If you put this in vinegar, this is going to take a lot longer to dissolve versus taking that particle, breaking it up into smaller pieces and putting it in the vinegar. This one is going to dissolve or weather a lot faster. So in our station work the other day, when you were using the Alka-Seltzer and putting it in the water and watching the dissolving occur, if you were to take that same Alka-Seltzer tablet and break it into smaller pieces, that dissolving would have occurred faster. The last factor that affects the rate of weathering is the mineral composition, meaning what minerals are in the rock and also what types of rock that they are. One of the things we've learned when our mineral unit is that minerals have different hardnesses, meaning the resistance to scratching. And if your minerals are softer, they're low on the Mohs hardness scale, they're going to scratch easily. They're going to break down easier. And minerals that are harder are going to resist that scratching. They're going to resist breaking down. And one of the things you do want to remember is that quartz is the most resistant mineral. And so we have granite that has quartz in it, but the other minerals that are in the granite will break down over time, but quartz crystals will be the last ones standing, so to speak. So in this picture, we've seen this before. We've seen these map symbols on page 7 of our reference table. So if you would get to your page 7, your reference table right now, and take that out, we can talk about these rock layers that are here. And if you remember this little speckled symbol here, that was our sandstone, this was our shale, and this was our limestone. And this is representing some sort of igneous. And one of the questions that you'll be asked often is to determine which rock layers are the most resistant, meaning which ones are not weathering, which ones are resisting the breaking down and into smaller pieces and then eventually being carried away by erosion. And so in here, if you were to look, you just look at, here's the surface, and this would be the atmosphere up here. And if you're going along the surface, which one seems to be weathering faster than the others? Which one's the least resistant? And when you're looking along, you might see this little dip in the landscape. This is indicating that the shale seems to be weathering more than others. It's the least resistant. It's breaking down faster. So here, let's practice a little bit more. We have some Regents level questions here for you. This was on a past Regents exam, and it gives you some background as to, this is a portion of an escarpment that's in Thatcher State Park near Albany, and the rock formations are identified. And some of them you might actually see and say, hey, I know those places, like Marcellus. This is the Marcellus Shale that people are trying to mine below our area, but here in Albany, it's at the surface. And if you go through, it says, which formations appear to be the most resistant to weathering? Most resistant, meaning it's not breaking down. So if we look at these, so if we were to look at our choices here, we would look at this choice here, number 1, which I'm not going to try to say, which is right up here for you. So you take a look at that and see how much is actually there. The next one is down here. You can see that there's more of it. It seems to be more resistant than the one in choice 1. Marcellus and Hamilton here at the top, not a lot there. So if I had to put these in order, this is the least resistant right now, and this would be our most resistant. And then let's take a look at this Schenectady one, which is right down here at the end, and this is farther out. There's more of it than the other rock layers. So choice 4 would be our answer right here, choice 4. And then this is, of course, a review question that kind of was a part of this question on a Regents exam. It says, what is the main factor that causes bedrock to weather at different rates? And here you can see our answer is mineral composition, because that's one of the 3 that we were discussing. We've talked about the climate of the area, we've talked about the particle size of those fragments, and also the minerals that are found in the rock. So to finish up with another example of a question, here's another example of a Regents level question. Which sandstone layer appears to be the least resistant? So this is opposite of the other question. So now remember, you're looking for the one that you don't see a lot of. And they're all here sandstone with different cements, but the one that has the calcite cement seems to be the least resistant. And one of the things you could imagine is that if the area has heavy rainfall, that slightly acidic rain is going to attack that calcite that's keeping those sand grains together. So here you have a great example of a artifact that was once buried below for over 3,000 years below the surface. This is called Cleopatra's Needle. It's an obelisk that has all the hieroglyphics on here. It fell over in Egypt a long time ago and was uncovered, and there's 3 of them given to 3 different places. One is in Paris, one is in London, and one is in New York City. The one over here is the one in New York City, and you can see how the surface has changed. That you take this particular rock, which is, I think, a granite, and take it to a climate that has more rainfall and warmer temperatures, and you're going to see this slowly eating away. The chemical weathering is higher in this area compared to over in the area of Egypt where it was originally from, and now they're slowly dissolving the surface of those hieroglyphics. Here's the one in Paris, same obelisk, but you can see some maybe even tried to protect, maybe polished, maybe put some separate chemical on there to help protect it from the chemical weathering that would be occurring there as well. All right, our last little slide here is products of weathering. One of the things we need to remember is that this whole process of weathering is really important to the earth and to us humans living on the earth, because it takes those rocks and breaks them down into smaller sediments, and it also releases some of the minerals that are within those rocks that we then will make their way into water, into our water table, and that we ingest and need for us. But it also creates soil. Soil is really important for our survival. Without soil, there really would be no life. And the last thing is that this process of weathering can also create some really spectacular landforms for us to go and observe and watch. So this concludes our video on the rates of weathering and the products of weathering. And remember, the 3 factors of weathering are climate, particle size, and mineral composition. And those 3 things determine the rate at which a rock will be weathered, how fast or how slow. And that in a climate with lots of rainfall and high temperatures, you'll have a strong chemical weathering. And an area where it's dry and temperatures can be warm or cool, but the dry is the important part. The lack of rainfall, you're going to have more physical or mechanical weathering occur.